Imagine living in a city where the ground is literally sinking year after year. In Mexico City, buildings, avenues, and even subway lines are sinking into what was once a vast lake. In some places, the ground has already dropped by more than 10 meters over the last century. What makes one of the biggest megacities on Earth be built on top of an ancient lake? And how does that choice, made hundreds of years ago, still force engineers to dig megatunnels, pump entire rivers underground, and fight the risk of collapse? Welcome to Invisible Structures. Today, you're going to discover why Mexico City is, at the same time, an engineering masterpiece and a slow-motion geological disaster. A city built over the ancient Lake Texcoco, now paying the price for trying to dominate water and soft ground. The story begins before the skyscrapers, when the Aztecs decided to build Tenochtitlan in the middle of that lake, using artificial islands and canals. Centuries later, the legacy of that choice is still hidden beneath the modern asphalt, in drainage tunnels, underground reservoirs, and the subtle cracks in house walls. And the most astonishing part is that, even with all today's technology, Mexico City is still sinking. The question is, for how long? Before we dive into the invisible systems that keep this city standing, go ahead and subscribe here to Invisible Structures. That way, you won't miss the next episodes. And tell me this, would you dare live in a city that is disappearing centimeter by centimeter? Because down here, nothing is completely solid. Picture the landscape before the buildings and avenues. A chain of lakes surrounded by mountains. The largest was Lake Texcoco, shallow and wide, exactly where some of the densest parts of the metropolis stand today. When the Spanish took Tenochtitlan, they looked at that city on the water and did the opposite of the Aztecs. Instead of living with the lake, they decided to drain it. They opened canals, dikes, and cuts through the mountains to create an artificial outlet for water in a basin with nowhere to drain. Over the centuries, that interconnected lake system was forcibly turned into dry land. But that dry comes with a huge asterisk. Beneath the city, there is no solid bedrock, but a thick layer of wet lakebed clay, formed by fine sediments at the bottom of the lake. Imagine walking on a mattress of mud and water. It seems solid, but under constant weight, it slowly sinks. Now replace your weight with the weight of an entire metropolis. That is exactly what is happening to the city. For a long time, that compression was slow. But with the population explosion of the 20th century, the subsoil became a giant reservoir. Enormous volumes of groundwater began to be pumped out to supply millions of people. Every liter removed empties the pores in the clay, which loses support and compacts. The result? The ground drops. In some areas, total sinking has already passed from 9 to 10 meters. And today, some zones still sink between 5 and 40 centimeters a year. The city is not just crooked. It has changed elevation from its past. Historic buildings needed reinforcement and extra stairways because the original floor level sank. Streets that used to be flat developed steps, ripples, and tilted sidewalks. The city map gained an artificial topography, created not by mountains, but by this slow, continuous sinking of the ground, what geologists call subsidence. Now add that soft soil to one more detail. The basin where the city sits has no natural outlet for rainwater. During storm season, everything depends on artificial drainage. First came open-air canals. As the city grew, massive collectors and underground tunnels followed, like the deep drainage system and the central outfall, inaugurated in the second half of the 20th century. These systems were designed to work by gravity. Water enters at a higher point and flows downhill until it leaves the valley. The problem is that when the entire ground shifts, that slope disappears. In some places, points that were supposed to sit above the outlet have sunk so much that sewage and stormwater can no longer flow on their own. It is like having a bathroom drain, but the floor around it sinks lower than the drain itself. To prevent catastrophic flooding and relieve the old tunnels, one of the largest underground projects in the world came into play: the Eastern Emission Tunnel, or TEO. It is basically a buried artificial river, about 62 kilometers long, with an internal diameter of 7 meters, carrying water and sewage as deep as 200 meters underground. To picture it, a tunnel so long it cuts across the metro region, invisible, carrying away up to 150,000 liters of water per second toward treatment plants and neighboring valleys. Along the way, the mega drain is reached through dozens of vertical shafts, known as lumbreras, some as deep as 150 meters. Each one is a gigantic chimney through which machines, crews, and the flows that must be evacuated from the basin all pass. This underground infrastructure does not just get water out of the way. It also works as insurance against the sinking itself. As the ground drops and deforms shallow pipelines, the Eastern Emission Tunnel and other deep tunnels take over as the main route, where deformations are smaller and the concrete and steel lining keeps the profile stable longer. Without these structures, any season of intense rain could turn avenues into permanent rivers and force the city to relive, against its will, its past as a lake. If you are already amazed by the idea of an entire city depending on hidden tunnels to keep from turning back into a lake, leave your like here. That lets me know you enjoy this kind of deep dive into the structures nobody sees, but that hold together the daily lives of millions of people above an ancient lake bed. Even with all of this, the battle is far from over. This sinking does not happen the same way in every neighborhood. Some sink more, others less, creating stress in pipes, rails, and foundations. At some intersections, the sidewalk looks melted, and the asphalt folds into waves. A lot of people think the city's biggest enemy is only earthquakes, when in reality, the water pumped from below, combined with clay soil, is a silent and constant villain. When you walk through Mexico City today, the sinking is visible in the facades, the crooked sidewalks, and the cracks that split entire houses. In some neighborhoods, residents have already grown used to doors that will not close properly, misaligned windows, and walls that seem to have melted over time. The real villain is not just that the ground sinks, but that it sinks differently in each area. That phenomenon, when one part of a neighborhood sinks more than another, is called differential subsidence, and that is what truly destroys structures. One part of the block drops a few centimeters a year, while the next block sinks a little more or less. That difference creates bending and cracks in everything designed to sit on stable ground. It is like placing a house on a mattress with invisible holes. Sooner or later, it tilts. The result shows up in symbolic places. The Metropolitan Cathedral itself in the historic center has been settling for decades. To keep the building from tipping over, engineers installed reinforcements, injected materials into the subsoil, and continue to monitor the foundation. Even so, the ground keeps sinking slowly. But the drama is most dangerous in everyday infrastructure. The water and sewage network suffers as the terrain deforms. Buried pipes, designed with a certain slope, end up developing invisible sags and steps. In some places, the pipe separates from its concrete base, leaving sections suspended. That leads to leaks, ruptures, and seepage that weaken the surrounding ground even more. Now imagine all of this beneath one of the busiest subway systems in the world. The Mexico City subway carries millions of people every day, and a large part of its lines runs right through the areas where the ground is sinking fastest. Studies show zones where this ground sinking reaches nearly 50 centimeters a year, one of the highest rates on the planet. For a rail line that needs to stay level, that is a slow-motion horror film. At some stations like Pantitlán, the problem is so obvious that it has made headlines. The structure sinks about 11 centimeters a year, creating cracks in columns, uneven platforms, and extra stress on the beams that support the trains. In other parts of the network, reports have identified sections where the rail was literally left unsupported because the slab gave way, creating gaps and shifts between elements that were supposed to work together. All of this in a city that also lives with earthquakes. In 2021, the collapse of an elevated section of Line 12 near Olivos Station laid that vulnerability bare. The causes involved design, construction, and maintenance failures, but in an environment where the ground is unstable, any structural flaw carries far greater weight. After that, several parts of the system began to be re-examined under a microscope, even using satellite data to measure how every column, viaduct, and tunnel is pulled downward year after year. And it is not just the subway. Entire streets show cracks that follow fault lines created by the sinking. In many neighborhoods, houses sit on a kind of improvised staircase. The lot in front sank faster, the one on the side street less, and the people living in between now deal with steps where there used to be a continuous surface. At some intersections, permanent puddles reveal where the asphalt turned into a basin. Not because anyone designed it that way, but because the ground gave way. Now, I want to hear from you. Would you live in a city that sinks a few centimeters a year? Leave your opinion in the comments and tell me what city you are watching from too. It is interesting to compare the reality of people living in stable regions with those who already see cracks, settlement, and flooding in daily life. From an economic standpoint, that uneven sinking is an invisible drain. Research estimates that hundreds of thousands of properties are already in high or very high-risk zones for damage from this uneven ground sinking, so-called differential subsidence, adding up to billions of dollars in threatened assets. It is not just a matter of fixing a crack. It means underpinning foundations, reinforcing viaducts, lowering pipelines, and rebuilding drainage. A costly, slow, recurring process. And the cruelest detail is that much of this deformation is considered irreversible. Even if the city stopped all groundwater extraction today, which is not simple because millions of people depend on that resource, the clay layers that have already been compacted would not return to their original volume. What has already sunk is gone. What can be done now is to control the speed of the process and adapt structures to survive on ground that will keep moving. Meanwhile, engineers and planners use satellite data, field sensors, and numerical models to map, almost in real time, where the city is most vulnerable. That makes it possible to prioritize reinforcements in subway sections, hospitals, major water mains, and densely populated areas. It is like having a heat map of the ground below, showing where the carpet is sinking fastest. At the same time, life on the surface goes on. People catch buses, step into the subway, walk past the cathedral, and work in buildings that are gradually a few centimeters lower than they were the year before. Down below, megatunnels, pumps, and sensors form Mexico City's emergency infrastructure, the invisible structures trying to keep this metropolis from literally becoming a lake again. Beneath those traffic-choked avenues, there is a second world, a network of tunnels, galleries, pumps, and sensors working like a giant circulatory system pushing water out of the basin. The system was designed as a modular set. Instead of one fully continuous, blind pipe, the Eastern Emission Tunnel is divided by inspection shafts and intermediate structures. If one section suffers deformation, crews can enter through one of those points, isolate that stretch, and make repairs instead of losing the entire system. In many of those shafts, the real spectacle is the pumps. They look like airplane turbines hanging from steel structures, each one capable of moving thousands of liters of water per second. When the level in the tunnels or holding chambers rises too high, sensors send signals to control panels on the surface. In seconds, huge motors are switched on, valves open, and the water is pushed out of the basin. For residents, what they see is the floodwater going down on its own. The system was not designed only for average rainfall. It was sized for storm of the century scenarios, when the equivalent of weeks of rain falls in just a few days. Without these megatunnels and pumping stations, the combination of sinking ground, paved over city surfaces, and no natural outlet for water would turn entire neighborhoods into permanent lagoons. And the more the city grows, the more it depends on this underground lung to keep breathing. If this kind of project amazes you, giant machinery, a tunnel 7 meters in diameter, colossal pumps at great depth, this is a great moment to leave your like on the video. That helps YouTube understand there are more people curious about these invisible structures, and it starts recommending more content like this to you. Beyond drainage, there are regulating reservoirs built in former lake areas designed to hold part of the rainwater for a few hours or days and release it gradually into the main system. The idea is to turn what used to be a natural lake into something like a controlled lake. Basins, dikes, and artificial lakes that take in part of the excess volume and ease the load on the deep tunnels. In the middle of all this come the fine surgery solutions, injecting concrete and resins into the subsoil to reinforce foundations, driving deeper piles in new projects, reinforcing viaducts, and rebuilding bridges and subway stations with more flexible supports, able to absorb small deformations. Every major new project in the city has to be a hybrid of civil engineering and applied geology. The result is a paradoxical landscape. Mexico City is one of the most geotechnically vulnerable megacities in the world, but also a laboratory of solutions for cities built on soft, sunken ground. What is being learned in the Eastern Emission Tunnel, in the deep pumping stations, and in the reinforced subway lines could one day help other megacities facing similar problems, whether from sinking ground or rising sea levels. Even with all this technology, nothing here is permanent. The pumps need power, the tunnels need maintenance, the soil keeps compacting, and millions still depend on groundwater pumped from below to live. The city lives in a delicate balance between its past as a lake and its present as a megacity, always just a few centimeters away from a new problem. On the surface, it behaves like any megacity: heavy traffic, tall buildings, shopping centers, Residential neighborhoods? But beneath that routine, the question remains, how long can a city built over an ancient lake keep defying gravity, water, and the ground itself? If groundwater extraction remains intense, this land subsidence will likely continue for decades. That means more settlement, more reinforcements, more costly projects, and hard decisions about where to invest first and what may have to be abandoned. At the same time, there is a growing movement to rebalance that relationship with water. Projects for artificial aquifer recharge, rainwater reuse, reducing losses in distribution networks, and even the idea of returning some spaces to their role as floodable areas are beginning to gain ground. It is as if the city, after centuries of trying to erase the lake from the map, is starting to accept that it will always exist in some form, even if invisible, hidden in the memory of the soil. Those long-term solutions compete with immediate urgencies. It is hard to convince the public to invest billions in tunnels, reservoirs, and monitoring networks when the problem is, most of the time, hidden beneath the asphalt. But in places like Mexico City, delaying those decisions only pushes the bill onto the next generation. If, in the past, the lake was drained in the name of progress, today some proposals speak of bringing the city closer to water again. Creating floodable parks, restoring parts of former bodies of water, and redesigning neighborhoods to live better with flooding may sound like a step backward, but it is often the smartest way to avoid even bigger collapses. Sometimes, the most advanced engineering is not the kind that eliminates nature, but the kind that learns to negotiate with it. To an outside observer, it may seem absurd to insist on keeping a megacity over a former lake that is constantly sinking. But when you think about the tens of millions of people who built their lives there, and the sheer amount of infrastructure, history, and identity involved, you understand why the answer is not simply abandon everything and start somewhere else. The challenge from here on is to make sure every new tunnel, every foundation reinforcement, and every water supply decision takes that unstable ground into account, and maybe turns that geographic past into an advantage of knowledge. And you, after hearing this story, what do you find more impressive? The fact that the city is sinking, or the massive effort to keep it alive on top of an ancient lake? Tell me below what surprised you most and what you learned from this episode. And if you have not done it yet, subscribe now to Invisible Structures and keep exploring the projects, the hidden workings, and the underground systems that hold up the world we see on the surface.